Okay, so where were we? We were... So last time we had done the proof of Green's theorem. No. Okay, so Green's theorem is this theorem that links together the two types of integrals we've been looking at. These integrals here on the left, which are integrals of a linear differential form, a p dx plus q dy, where the p and q are functions of x and y, integrating these around a closed simple curve. Curve C, which is closed, its endpoint is the same as its start point, and it's simple, it has no self-intersections along the way. Such as, for example, this kind of a simple closed curve. And these simple closed curves in the plane, they enclose simply connected regions. Regions without any holes in them. This region isn't simply connected. The shaded region, its boundary curve has two separate components, an outer component and an inner component. So that's not a simply connected region. So this is. So Green's theorem applies to regions like this, shaded regions like this. Simply connected regions with a simple closed boundary. And under certain conditions about the well-behavedness of the P and Q, they must have continuous partial derivatives both on the boundary and everywhere inside the region. Then Green's theorem asserts that these two integrals are the same. Okay. The integral on the left is the integral around the boundary, around the curve C, p dx plus q dy. The integral on the right is the double integral over the entire region of this difference between the two partial derivatives. Also, this assumes that C is traversed in the conventional direction, which is counterclockwise. Okay. If you did have C traversed in the opposite direction, clockwise, then this would change the sign. That would change the sign of the left-hand side. That would change the sign of the right-hand side, and this difference here would be dp dy minus dq dx. Okay. So the fact that there's a minus sign attached to one of these and not the other has to do with the choice of direction on the integrating around the curve C. Whether you go clockwise or counterclockwise. But counterclockwise is the default direction we like to go, and it's good if we do that as much as possible. It's like driving on the left. Best if everybody does the same thing. Okay, did I do example? I think I did do example. Did I do example 1.23? Yes, so this is going back to a previous example. So in the previous example 1.22, we did this integral of this around the square, the integral of this p dx plus q dy around the square. And then I think we did example 23 last time, where we worked out the right-hand side of Green's theorem and confirmed that this gave the same answer. Okay. So we're going to look at a couple of applications of Green's theorem now. The first one has to do with talking about the area of a closed loop. Area enclosed by a closed loop. Okay. In general, if you have the integral over a region R of dx dy, so this is a double integral where you're just integrating the constant function 1. Remember what these double integrals represent. These double integrals represent the volume contained in the region of three-dimensional space, bounded below by the xy plane, by the region in the xy plane, and bounded above by the surface whose height is defined by the function that you're integrating. But here, if we're just integrating a function with constant value 1, that means the surface we're talking about is the surface with constant height 1. So it's just an infinite horizontal sheet, 1 meter or one unit up off the ground. So the volume contained over any region of the plane, the cylindrical type of volume coming out from that region and bounded above by the surface, well, it's a cylinder with a cross-section of the region R and height 1. So that volume is going to be the same numerical quantity as the area of the region. Okay? So that general principle, if you take some region R as a cross-section and you look at the kind of cylinder shape formed, so if you have whatever kind of region and you look at the cylinder you get by extruding that kind of region all the way. So the cross-section here is always the shape, the region R. The volume of this thing is that whatever its height is, whatever the height is, the volume is equal to the height of it times the area of R. Yeah, that's what the volume of this kind of thing is going to be. Whatever cross-sectional area you have, just multiplied by whatever the length of the cylinder region you're taking. So where with a special case where we're always looking at a height 1, so to speak. So this could be the surface of constant height 1 above the xy plane. This volume is just going to be the same numerical quantity as the area of R. That's why, remember, we refer to this dx dy as the area element. Sometimes when you integrate the area element over a region, you accumulate the area of that region.
What's the volume?
The volume of this portion of space is the area of the cross-section, the area of R, multiplied by whatever height it is. Yeah, general principle. Yeah. Remember, like the formula for the area of a regular cylinder with circular cross-section is the area of the circular cross-section, which is pi r squared, multiplied by h. H being the height of it, yeah? R being the radius. Familiar formula for the volume of an actual cylinder, but it's just following this principle. So your more general cylinders will have the same kind of volume formula as well. So what we can do is, and what it lays out here in the notes, is we think about, well, how could we obtain this kind of thing here as a result of applying Green's theorem? And it can come about in many ways. One of the ways it can come about is if we integrate this linear differential form, x dy minus y dx. Well, this isn't the only one, and it's not the most simple one, but if we did integrate x dy minus y dx, okay, so our p is minus y, that's the function multiplying dx, and the q is just x, it's the function multiplying dy in the linear differential form, and we're integrating it around the boundary of the region R. Well, Green's theorem, so this equation here is the application of Green's theorem. We integrate the difference of the two partial derivatives. Okay, so you're taking dp dy and dq dx. You're doing dq dx minus dp dy. So that's what we're seeing here. But then this just comes to the value 2. Okay. So the 2 moves outside and just push the 2 to the other side, get a half, and you get that this integral, which we've just explained here, is the area of the region. This double integral of dx dy is given by a half of this integral of this linear differential form around the boundary of the curve. Okay, so this is an interesting. It's an interesting kind of thing. It tells you that you can calculate the area of a certain region in the plane by performing an integral around its boundary. Okay, which is a neat idea. It's saying that we don't have to go inside the region R to calculate the area. We can just calculate the area by just traversing the boundary of the region. And so there's an example given here, which we can look at. example 1.24. So, yeah, so the ellipse with equation x squared over a squared plus y squared over b squared equals 1. So this is an ellipse. To draw it in the plane, it's this kind of a thing here. Where it puts the x-axis at a and minus a, puts the y-axis at b and minus b. So we can obtain the area by integrating around E. Okay, the area enclosed by this ellipse, we can calculate that by integrating around its boundary. So what we want to do is do the closed integral around E, take a half of this linear differential form, which is x dy minus y dx. This is going to give us the area enclosed by E. Okay, well, what's a good way to do this integral? Well, a good way to do this integral would be to use the parameterization of the ellipse. So that's given to you in the question. So E is parameterized. And it's the same parameterization that the conventional one that the circle has. So the circle is parameterized by by x is cosine and y is sine of the angle. But for the ellipse, so the circle would be when a and b are both 1, that would be the unit circle. But for an ellipse, the ellipse is parameterized when the x-coordinate is instead scaled by this factor a, and the y-coordinate is then scaled by that factor b. So harmony is when a and b are both 1, then you got the unit circle. But when they're both scaled by these other factors, that gives you the ellipse. Yeah, this is with a and b both positive. But this is using this parameterization will be what allows us to actually evaluate this integral, because then we can translate it into an integral just involving t. So with this parameterization, the differentials will be, well, dx will be minus a times the sine of t, and dy will be b times the cosine of t. Okay. So we can get the associated differentials, dx and dy. So the area then becomes the closed integral around E, as we've said, of x dy, half of that, minus y dx. But then applying the parameterization, this becomes the integral from 0 to 2 pi. The t is like the angle going around the ellipse. And so the x is a cosine of t. That's multiplied by dy, which is b cosine of t. And then we're subtracting y, which is b sine of t, by dx, which is minus a sine of t. And this whole integral is done dt. Move it up a bit, yeah. Paper up, yeah. Down. Why did you say up there? You want to see the up bit of the writing. Yes, I understand. You make those mistakes. You just have to remind people it's a sign of genius that when you get things completely wrong. It's a well-known thing. I mean, it is near Christmas. Can I show a cartoon? It is near Christmas. Really quickly. Does everybody know the Far Side cartoons? You know the Far Side cartoons? I think this is the right one. So you should be proud of those moments when you get things wrong. Everybody got it? He's a gifted kid. He has to be. He's going to the school for the gifted. But he can't open the door.
All right. So I didn't realize the joke.
That is what we are all like. We should embrace it as mathematicians. Okay. Where were we? Okay, so let's embrace this. Okay, so you can kind of see what's going on. You've got AB, factorize out the AB, and you've got our familiar thing, cosine squared plus sine squared of t, dt, which is, of course, 1. Yeah, this expression, cosine squared plus sine squared is 1. And the AB is independent of t. A and B are fixed constants, so they can move to the outside. So it's just the integral from 0 to 2 pi of t, which is, of course, just the length of the interval. The dt, people will sometimes call that the length element. For in the one dimension, just as dx dy is the area element in a two-dimensional integral. In a single-dimensional integral like this, the differential can be called the length element as well. So it's just going to give you the length of this interval, which is 2 pi. So the whole thing comes to pi AB. Okay. So this is our formula for the area of the ellipse. Yeah. Oh no, indeed is the formula. Notice just NB. This gives the usual formula of the area of the circle. Pi r squared, because the circle is when both A and B are the same value. Both A and B on the ellipse are the same value, so if they're both equal to r, so you're talking about the circle of radius r, so again, this gives you the familiar formula for the area of the circle. There's also another thing I'll show you, not a cartoon, but the name escaped me for the moment, but I'll find it now.
No, it's not a cartoon. You're not
I've forgotten the area.
Just trying to find specific things we can talk about.
I'll try to remember it before the lecture ends. There's a device. So in the pre-electronic days, if you had maps, there's a like a physical device. It's a little roller thing with a wheel on it, And if you've got a map in front of you,
And
and let's say there was a field marked on the map, you can just run the wheel around the boundary of the area on the map, and then there's a readout on it. As you roll it around, it turns various dials and stuff, and it gives you a readout of the area of the curve, the area enclosed by the curve you've just drawn. It's a something meter. I'm just trying to remember the name of it. It's escaped me. But that applies Green's theorem, because you're calculating the area. You're calculating the area by running around the boundary of the area. But the only thing is now when you Google it, it all comes up as just how to do it electronically using. So I'm trying to find the pre-electronic version of it. Old maps area meter. What's it called? Sorry, I'll think about it. Oh, green. Parameter, that's it. Parameter. Yeah. So it's this kind of device here. So this is actually implementing Green's theorem. So this is a device which is attached to your table, and if you laid out some map underneath it, you see there's various scales and readouts, and there's some kind of a reference point on this end, like a sharp point, and if you use this to trace around a boundary curve on a map, okay, then as you move the thing around, there's various cogs and wheels in here, which effectively they carry out that curve integral, like what we just showed. As you move this around, these cogs turn and register the movement in the x and y directions and combine it together so that when you finish moving around the curve, the total readout on one of these is the area of the region that you've just gone around. So it's how people worked out areas of regions on maps in the kind of pre-electronic days. Okay. Sorry, I should have had that plan better. Anyway. Okay, so more or less the final section here is path independence and dependence. So this is something we went back to. This is something we kind of highlighted early on. So early on when we were doing path integrals or integrals over curves, we showed in a few examples where that if you took different paths between endpoints, so the same starting point, the same endpoint, if you followed different paths between them and integrated the same linear differential form along the two paths, in general you expect those to give you different answers. Okay? So you're integrating along different curves, you're moving over different points, you're evaluating the function at different points. In general, you expect that to give you different answers. Okay? But we did see some examples, I think, which showed that you got the same value. So sometimes you get the same value, but they're special. In general, when you integrate a linear differential form, in general, from a point A to a point B, in general, we expect to get different answers. So it's a different integral. But there's a special case where we will always get the same value. And again, this is an application of Green's theorem. So the special case is when the linear differential form p dx plus q dy that you're integrating satisfies this, okay? Where the y derivative is the same, the y derivative of p, dp dy, is the same as the x derivative of q, dq dx. Now, the significance of that, of course, is that when these two are the same, this means the right-hand side of this integral is 0. Okay, the right-hand side of this integral is 0. So, how does that prove it? So let's have a look at this. So we'll give a sketch of the proof of this. a sketch of the main idea. So here's our 2 points, A and B. Here's one curve between them. C1, here's another curve. C2. Okay. So you might have 2 curves like this. Okay. But consider the curve C, which is equal to, so let's go C1 minus C2. Remember, minus a curve means traverse the curve in the opposite direction to whatever original direction it has. So the curve C1 minus C2 means go along C1 and then traverse C2 in the opposite direction to the direction that C2 has. So this curve C, well, at least for these curves, if C1, C2 are non-intersecting of each other and themselves, then C is a simple closed curve. So if both the curves C1 and C2 have no self-intersections, and they also don't intersect each other, then when you run the two together, like C1 minus C2, you're going to get a closed simple curve. Okay? A closed curve because you're starting at A, and you're returning back to A. And it's going to be simple. We'll have no self-intersections because neither C1 nor C2. And then there's this region enclosed by them. C is a simple closed curve enclosing the region R. The simply connected region R. Well, so in that case, we can just throw Green's theorem out. Yeah. So the integral along C, p dx plus q dy will be equal to, by Green's theorem, the double integral over R of dq dx, not the way it goes, dq dx minus dp dy. But this is equal to 0 if dq dx is equal to dp dy as in the theorem. Okay, the theorem says the conditions of the theorem says they're equal. If these two are equal, then this integral will be 0. Okay. But this integral on the left-hand side, the closed integral around C of whatever, is the integral along C1 plus the integral along minus C2. Because those are the two, we can subdivide the curve C into the two halves, C1 and minus C2. But remember, a property of integration is if you change the direction of the curve, so instead of going along minus C2, go along the curve C2 with its original direction, then you change the sign, you change the sign of the integral. So adding the integral along minus C2 is the same as subtracting the integral along C2. And so if these are both equal to 0, this implies that the integral along C1, or whatever, equals the integral along C2. So this is our p dx plus q dy. So it's a consequence of Green's theorem. But that was a special case that the two curves C1 and C2 had to be nice like that, had to not intersect themselves and not intersect each other. So what might the general case? So this is a special case first. Special case of two nice curves. what might the general case look like, and how different is that to this special case? Well, the general case would be that I have my 2 points A and B, and we're talking about 2 different paths between them. Well, okay, so I could have a self-intersecting path, C1, and I might have another self-intersecting path that also intersects with C1. So I might have I should have drawn them in different colors, but look at where there's no sharp corners in these things. So this is C1 coming this way, C2. Okay, so the same argument we had before does not apply simply because it's not a simple closed curve when you run C1 minus C2. But in this case, the integral along C, so if we take C as being C1 minus C2, the integral along C can be divided into a sum of integrals like the special case. So what am I talking about there? Remember, one of the properties of integrals along curves is you can, subdivide up the curve in any way, and subdivide the integral as the integral along this bit of the curve plus the integral along that bit of the curve, and so on. So if we want to integrate along C1 and come back along C2, well, for instance, in these small little loops, we could just make the curve, we could just consider the integral just around these little loops. So we could look at all these points where we've got these intersections, and we could decompose the whole thing into just a collection of sorry, I made my loops a bit small. You get the idea. You could go, which way is this going? This is coming, you're going to go minus C2, so we'll come back here, go this way. So if you want to integrate out along C1 and integrate back along C2, okay, you can do that. That's the integral over C. But that can be split up into, well, a bit of it is just doing this integral here, which is a simple closed curve. I just go on and I avoid any things like that. But then, see, we missed out this bit, so we'll have to have this bit as its own little integral. But that on its own is a simple closed curve. This bit on its own going this way is a simple closed curve. It picks up this bit of C1 and this bit of minus C2. But that can go in its own integral, simple closed curve. This can go in its own integral, simple closed curve. And this bit can go in its own integral, simple closed curve. So the integral along the whole of C, we just subdivide it up into these smaller simple closed curves. And the integral along C can be thought of as the integral, along these small curves. Let's just put it like this. It's to abuse the notation, but this is just representing the sum of the integrals along each of these small little simple closed curves. Oh, sorry, we don't have that there. We're not multiplying them each by a curve. No, just the sum of the integrals along each of the little blue curves, and you're summing over all the little blue curves. Okay. And each of these is like the special case, because each of these is a simple closed curve. So for each small blue curve is a simple closed curve. So that's a sketch of the proof of that theorem. Okay. So we have this criteria for path independence. Path independence was this property of certain integrals, certain linear differential forms, when it didn't matter along which path you made the integral, between a certain start point and a certain end point. So the criteria for path independence then is that dq dx equals dp dy. Okay, so we can recognize path independence of the linear differential form. Okay, we'll leave that there for now, and I'll meet you again